In this video, we'll introduce the concept of an artificial neuron, which is going to be the basic building block we'll be using to construct complicated neural networks. So an artificial neuron is simply a computational unit which will make a particular computation based on other units it's connected to. So in the case of a single artificial neuron, like this one here, it's going to be connected directly on an input description of some object we want to extract information from. So this input description, we'll call it X. So here bold X is essentially a vector which contains the scalar x1 up to xd, where d is the size of the vector. Okay, so notice that I'll be using bold as when I'm denoting vectors and matrices as well, and whenever it's not in bold, then it corresponds to a scalar value. Okay, so xi is the ith element of vector x. And so this artificial neuron is going to read the information from this x vector and perform a particular computation which will dictate its value, the value of the neuron. And this value will essentially indicate whether some particular feature or information about this object that we're manipulating is present or not in the object described by the vector x. Now, the computation it will perform can be decomposed into two steps. There's going to be first the computation of a pre-activation of the neuron. Sometimes when you look at the literature, you see the expression instead input activation, but I'll avoid using input activation because for X we often use also the the word input to describe it. So instead I'll talk about this as the pre-activation. And the pre-activation, which I'll note A of X for a given neuron, is simply going to be some scalar B, which we're going to refer to as the bias, the neuron bias, plus the product between a weight vector W with some the input vector X. So we can write it into vector form here, or we can write it into a more scalar form where we have B plus the summation over all I, so all indices within the vector of the ith element of W times the ith element of X. And then from this pre-activation, the neuron will compute its activation, which is sometimes referred to as the output activation of the neuron, by simply taking the pre-activation and passing it through a activation function. So this g function here is what we're going to call activation function, and there are going to be different choices of potential activation functions we will be able to use. So the output activation, I will often note it as h of x, and that will be the activation. If I don't say output, if I just say activation, I mean the output activation of a given neuron. And so if we just put the expression for a of x explicitly, it will be the activation function applied on this linear transformation of the input vector made of the elements xi. So W, we will refer to it as the vector of connection weights, and that's because as in this visualization here, we can think of the elements of W as the strength of the connection between the neurons to which our neuron is connected to. In this case, these neurons would be input neurons. They would be neurons that take the value of each of the element in the input vector. So W will be the vector of connection weights. B will be a bias. It's a bias because it's if we have no input, B would be the pre-activation. So by observing a particular input, then we are essentially going away from this initial value B of the pre-activation of the neuron. And then, as I said, G will be the activation function. So here's a 2D visualization of the activation of a neuron. So imagine we have a vector made of two elements, x1 and x2. And then we'll note as y, so I could have written instead h of x here, as the output activation of the neuron. Okay, So the first thing we see here is that on this axis here, we get values that are between -1 and 1. And that will be because in this specific example, the range of values we can get once we pass the pre-activation through the activation function is a number between -1 and 1. And now what we see is that for different values of x, we get a different output. And specifically for all the values that lay here, we get an output for the neuron, an activation of -1, or very close to -1. And for all values of x here, we get a value of 1. So in this particular case, we have an artificial neuron that detects whether some given input point, x1, x2, belongs to this part of the space or this part of the space. So you can think of it as the artificial neuron as a binary classifier that separates points in one region and some other region. For now, we won't discuss how we actually find the parameters of the neuron that determine what regions it's actually separating. So for now, we'll just assume that someone has given us the value of the weight vector W and the bias vector B, which determines the shape of this function. And we'll see how we can actually have neurons that will train to discover good values of these parameters. So for now, we'll just assume that someone has given us these values. Also, geometrically, it turns out that the vector W will actually be perpendicular with respect to the hyperplane in the space that separates these two regions that the neuron is distinguishing, is separating. So this vector W determines essentially the orientation of this ridge between the two parts of the space that the neuron is separating. And then the bias B will essentially determine along this direction where the ridge will be. So if the bias is large, so when the bias is increasing, then the ridge will be moving in the opposite direction of W. So this would correspond to a perhaps negative value of B. And if we have the more strongly positive value of B, then the ridge would be moving in this direction. Okay. So I won't exactly explain why this is, but you can sit down and try to figure out why it is that W is perpendicular to this ridge, and why is it that when B is increasing, then the ridge would be moving this way. So this is the description of the computation that the artificial neuron is performing.